This, as we were saying, it's like a game of survivor. It always reminds me of the story all the time. There was this movie from in the 1980s called Real Genius or something like that. And like, it is a lot going on, but one of the things, the running joke in the movie is, it sort of takes place at folk Caltech or something. So the first day of class, and the classroom is filled with people, and everyone's really, really excited, and the professor is really excited. And as the course of semester goes on, there's fewer people. At that time, in order for people to, get the lecture information, they would have a tape recorder, a cassette recorder they put on their desk. This is actually whatever people did, but it did happen in the movie. And so, eventually the classroom was, more and more replaced with tape recorders and fewer students. And like the penultimate scene, it's all tape recorders, and the professor is just lecturing to tape recorders. And in the very last scene, the professor's a tape recorder talking to other tape recorders. So anyway, let's hope we don't get there.
Was this a movie you said, or?
Yeah, it's a movie. It's called Real Genius. Yeah, it's a great movie. All right, so let's see. So we're a number of announcements to make. So we have the problem set due today. So it was requested, I'm just mulling, that we're about a half a lecture behind where we wanted to be for relative to the homework. If it does need an extension, the answer is yes, you really do. The problem is bunching. We do this, the next assignment, and this is my concern. We have an exam coming up. I want you to be able to do this work in a reasonable way. But if we extend to Monday, we have to think about problem set 8, which is coming. And we gotta get the stuff to do, places to go, physics to see. But let's cross that bridge, okay? So we'll see Monday.
Thanks.
You're good. All right. Actually, it maybe makes more sense to say Friday, doesn't it? Yeah, it does. I'm sorry, but because then we can. It's a compromise. Okay.
Can you still release the next homework tonight?
I will. Yeah. Okay. Compromise. Okay. All right. Very good. So we're talking about propagation of electromagnetic waves in medium. In particular, last time we talked about linear dielectrics. Okay. So a linear dielectric is a material that only has bound charges. Okay? And so we think about it as an insulator. So when we start with the macroscopic Maxwell's equations, then we need what's called the constitutive relations, which relate the bound charge density and bound current density to the fields, and in a linear medium, the displacement and magnetic fields are related through epsilon and mu, okay? And the fact that the displacement and the magnetic field are instantaneously and locally related is to say that this is dispersionless, okay? Because as we will remind ourselves, really the polarization density and thus the displacement depends on the frequency of the field, okay? The fact that there's no frequency dependence here is to say it's dispersionless, and we'll talk more about that today. all right? So, very good. All right, so when we plug this into Maxwell's equations, we get this, setting the free current and charge density to be 0, we get these expressions for how the fields are related, and they look just like the Maxwell's equations in vacuum, except for this one modification, right? If we were in vacuum, this would be 1, but otherwise the only difference at this point under all these conditions. All right? And then when we do that, we find that we can take these equations, decouple them in our usual way by taking the curl of the curl and using vector identities, and we arrive at the wave equation for E. And equivalently, if we did the same thing for B, we get the wave equation for B, which is a wave equation in 3D, 3 dimensions, where the only difference that we had from the wave equation in vacuum is the modification of the phase velocity. Whereas, so in the vacuum in free space, as we call it, the phase velocity was c, the speed of light. Now it's c divided by the square root of mu times epsilon, and this factor, the square root of mu times epsilon, is known as the index of refraction, okay? It's what gives rise to the refraction, Snell's law, and the like in optics, okay? So optics follows the Maxwell's equations. All right, very good. So again, some things that we we did last time to remind you of, we can derive also the various relationships of the field by assuming a plane wave form. So plane wave solutions are generically of this form. And when we plug these ansatz, these guys generally could have complex polarization. So I'll put a little tilde there. It could be linear polarization, it could be circular polarization, it could be elliptical polarization. And when we plug these into this equation, we get that minus the magnitude of k squared plus omega, mu times epsilon over c squared, omega squared times E0 or B0 e to the I blah 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 is equal to 0, which tells us that omega is equal to c squared over mu, or c over square root of mu times epsilon times k. All right? And that is known as a dispersion relation. The relationship between omega and k for a plane wave is known as a dispersion relation, because it tells us something about, if we have multiple frequencies, how the wave disperses. That's what we'll discuss today, okay? And what this tells us also, it's always the case that the phase velocity of a plane wave, just looking at this form, the phase velocity, the velocity with which a point of constant phase propagates is always equal to, for a plane wave, omega over k, okay? And omega over k here is c over, just as we wrote up above here. Okay? So that's what we had. And moreover, Maxwell's equations written here tell us about the relationships between the different parameters. So the fact that del dot E equals 0 tells us that the electric field vector is perpendicular to the k vector. This equation tells us that the magnetic field is perpendicular to the k vector. So the fact that this is true, we call these transverse waves, that the wave oscillation is transverse. And these equations tell us that relationships between the E and B vectors, right? And so what we have is that the B vector is equal to C K over omega crossed into E naught, and K is equal to the index of refraction times omega over c in some direction, right? Because it's omega over the phase velocity, and the phase velocity is c over n. So this is equal to the index of refraction and the direction of it. So the magnitude of E does not equal the magnitude of B in the material. Their ratio depends on n, okay? And so the other things that we had was that the energy in the electric field, the energy density is given by this expression, and the energy in the magnetic field is given by this expression. That's the energy density, or equivalently this expression. And the Poynting vector is equal to E cross H times C over 4 pi. And we found last time that so in a plane wave, given what we have is that the mean energy density here is equal to epsilon naught over 16 pi times the amplitude squared. The energy density in the magnetic field is mu over 16 pi H0 squared, or right, this one, 1 over 16 pi mu B0 squared, which is equal to the index of refraction squared of 16 pi B0 squared, which is equal to the energy density in the electric field and the magnetic field are equal in a plane wave, even though the amplitudes are unequal. And what we also had was the intensity was equal to the phase velocity times the total energy density in the system. Okay. So this is everything we did last time, just to go through it again and have it firm in your minds. Okay. Does anybody have any questions about any of that? Yes, no, just raising your camera, not your hand. All right, very good. All right, So let's now talk more generally about the case where we do have dispersion, okay? So more generally, we can look at solutions for monochromatic fields, which means fields that are oscillating at a single frequency. That's what it means to be monochromatic. And we can always write any monochromatic field as the real part of some complex amplitude at that position for a given frequency. So this is a general form of any field that is oscillating at a single frequency will always have that form, okay? And similarly for, say, B or H or D. Moreover, if we have a linear scalar dielectric, meaning that the direction of the polarization is in the same direction as the electric field. So I'll just take it to be a scalar. So that is what it means to be a linear dielectric. And the fact that this is a number and not a tensor is what I mean by it being a scalar. So this is saying that the induced density of dipoles is linearly proportional to the electric field. And the proportionality constant is called the susceptibility. How susceptible is the material to being polarized? And similarly, there's some magnetization which has some magnetic susceptibility. And it's by convention defined proportional to H, not B. Yes?
Linear doesn't imply that's a scalar, right? It's
No,
just-
I'm saying it's also scalar.
Okay.
That's just an additional condition I'm giving to the materials. So with that, we have that D, the complex amplitude of D is epsilon E. And B, complex amplitude, is mu times H. Okay. Moreover, if we had unbound charges, we can have current. And the current that is flowing in the material that is oscillating at some frequency omega in the Drude model is proportional to the electric field. By the way, epsilon, by definition, is 1 plus 4 pi chi, and mu is 1 plus 4 pi chi magnetic. Okay? The Drude mode. Yes?
Here, P, I, and E, all of them are complex, right?
Everything is complex.
So what does it mean when I multiply two complex quantities together? Like, what does it physically mean?
Well, we'll talk about the physics of this in a moment, very soon. But at the moment, this is a mathematical relation. This is a complex number. That's to say, it's a complex vector. Each of its components are complex. Let's just remind ourselves what it means for this to be complex, okay? What it means for this to be complex is that it has an amplitude and a phase. If it has an amplitude and a phase, then it's saying the the oscillating field has some amplitude and some phase. Equivalently, it has, I can write, so if I have some complex, some function which is oscillating as a function of time with some frequency omega, this is the most general form of that function, which I can always write as the real part of e to the I phi times e to the minus I omega t. Right? And this is the complex amplitude. So the fact that this is complex is saying something about the amplitude and phase. Or equivalently, I can write this as A cos omega t plus B sine omega t, where A, little a, is A cos phi, and little b is A sine phi, which is the real and imaginary part of the complex amplitude.
So if I multiply by.
Yep. I'm gonna get real and imaginary parts. If I multiply two complex numbers together,
So complex time multiplication basically means I'm introducing another phase.
that's correct. So what it's saying is that both the amplitude and phase of this oscillating dipole is both modified in amplitude and modified in phase. There's a phase shift, yeah, as well. And that is to say, if it's oscillating like cosine, the response function, let's say the induced dipole, is not oscillating also as cosine. It will have a part that's also oscillating like sine. And we'll see what the physics of that, why that's important in a moment. Excellent. All right. So with all of that said, we put this together, and finally, we also said from the fact that del dot J is equal to, from the continuity equation of the free charges, that we can neglect the free charge density when omega, when for this being large. So given all of that, we can plug that into Maxwell's equations and get the following equations. We get del dot E tilde is 0, del dot B tilde is 0. We always have that del cross E is equal to I omega over C B tilde. And using all of these relations, which are called these relationships between the fields and the induced dipoles or current, are known as constitutive relations. There's something about the material. All these relations. What constitutes the material. That's a phenomenological thing. Gives us that del cross B tilde is equal to 4 pi over C mu tilde sigma tilde E tilde. That's 4 pi over C times J, and then we have minus I mu tilde epsilon tilde over C times omega B tilde. How did I get this? I plugged in this ansatz, that it's oscillating at that frequency omega. I plugged those equations into Maxwell's equations. Wherever I saw d by dt, I replaced it by a multiplication of minus I omega. and then use all the H and all the other stuff, and I get these relations. So you can, this is sometimes called Maxwell's equations in the frequency domain, okay? So once again, we can do our famous curl of curl equation. And using the fact that del dot E is 0, that's the Laplacian of E. And that's equal to the curl of that. So that's equal to 4 pi over C mu times sigma minus I mu epsilon omega over C times the curl of E. Okay. So I just took the curl of this, and I have to multiply that by minus I over C. So I can multiply this all by I times omega over C. Okay. So I took the curl of this, that becomes I omega over C times the curl of that, but the curl of that is this, and I plugged it in. Okay? And the curl of this is equal to I is it a sign wrong here? Oh, sorry. Okay, never mind. There's no event. Yeah. I just take the curl of that. That's all good. The curl of E. Ooh, doing this. Okay. Let's take it one step at a time. That's equal. Okay. I'm going to start again, because I'm going to lose my signs. This is equal to I omega over C, the curl of E, which is, I multiply that by that, and I get equal to I 4 pi omega over C squared times sigma times mu times E, and then I get plus mu epsilon omega squared over C squared times E. Good, that's correct. Okay, so this equation tells me that minus del squared E, complex amplitude, is equal to mu epsilon over C squared omega squared plus I 4 pi omega sigma over C squared times mu all times electric field. Okay, I think I did it right. So if the conductivity were 0, we're back to where we started, but with a complex, generally now a complex index of refraction. But we're also allowing ourselves to have some free current if we have some kind of conductor, okay? So this is the general form of the electric field, satisfies this with the constraints if I have a monochromatic field and these constituent relations. Now, the next question is, if I have a plane wave solution, what is the relationship between omega and k? How would I find that? That's right. So I assume if I have a plane wave, then the complex amplitude at some position is equal to e to the I k dot x. And similarly for b. So with that ansatz, as Colton said, I could just replace my del with I times k, which is equal to minus k dot k, or k squared. Everyone clear on that? What I did? I replaced the gradient by the I times k, and then I got that. Now notice, so now if this is true for all positions, then this, I can cancel this. And I get a relationship now between omega and k. It's a much more complicated relationship than we had before. Before we didn't have this term, and these were real numbers, and we had k was equal to, omega over the phase velocity, which was given by c over the square. But now we have this, okay? Now, one thing to notice here, so let's put this on the new board over here, is that this wave number k must be a complex number, right? This thing has real and imaginary parts. So k itself is a complex number, okay? In this most general form for this kind of material. So we have k is complex number. And it's equal to the square root of let's let me write it this way. It's equal to the square root of mu times epsilon plus I 4 pi sigma over omega times mu times omega over c. Okay, I factored out omega over c, which is equal to the complex index of refraction, which depends on frequency. I'm defining this to be the complex index of refraction. If I didn't have this term, and these were real, it's what we called the index of refraction just 10 minutes ago. Okay? But now I have an index of refraction which is a complex number. Okay? So this is equal to the real part, I'll call this where I've written the complex index of refraction as having a real part and an imaginary part, which I'm just calling n sub r and n sub I. So these are the real and imaginary parts of this complex number. Now, how the hell do you take the square root of a complex number?
Put it in e to the power of.
Right, you put it in polar form. The square root of a complex number z is equal to the magnitude. If I write this, so that's equal to the square root of the magnitude, and then it has half phase. You know, we did this sometime in our lives, but we maybe forgot it. Right? Okay, so what does it mean to have a complex index of refraction and therefore a complex wave number? Well, let's go back to our ansatz, okay? The amplitude really here, this wave vector is in this complex representation, it has a direction, but the magnitude is actually a complex number. So if we look at, let's suppose so I'll write the wave vector as the complex, it's in the z direction, okay? So that tells me that e to the I k dot x is equal to e to the I k tilde z, right? Which is equal to, so that tells me that e to the I k dot x is equal to e to the I n times omega over c times e, where n is the index of refraction, which is complex, which is equal to e to the I n real, and then I have I times n imaginary, and I times I is -1. And I'm just going to factor that out. Okay. So if I look at the say the electric field as the real electric field as a function of position and time, what is it? So let's suppose linear polarization. Make it simple. The electric field as a function of position, in this case it only varies a function of z and time, is the real part of the polarization vector, the amplitude, e to the I k tilde z minus omega t. Right? Which is what we just wrote down over here, the real part, so epsilon, we'll just bring that out. This is all real. It's the real part of e to the minus the imaginary part of the index of refraction, omega over c times e to the I k, or times e to the I n real omega over c z minus omega t. Right? What is the real part of this? This times this.
The decaying exponential times cosine.
Times cosine. This is real, so it comes outside, and the real part of that is cosine. So this is then equal to E0, e to the minus the imaginary part of the index of refraction, times the cosine, and I'm going to rewrite it in a slightly different way. Everyone see that? So what do we learn from this? How do we interpret the physical meaning of the real and the imaginary part of the index of refraction? Well, the real part tells me about the phase velocity. Notice that this thing is moving at the velocity c over the real part of the index of refraction, right? This is equal to c t minus z over the phase velocity, where the phase velocity is equal to c over the real part of the index of refraction. The real part of the index of refraction tells me about how the wave is propagating in terms of how the phase is moving, right? Whereas the imaginary part of this tells me something about how the amplitude is decaying. Right? And if I were to ask about what is the intensity of this wave as it propagates in the material, what would you find? If you look at this, remember that the intensity depends on the square of the amplitude, but the square of the amplitude is decaying, as opposed to in a plane wave, you have constant intensity. So in this medium, the intensity as a function of propagation into the material is whatever it is at z equals 0 times some decay constant, let me call it beta, where beta is equal to twice the imaginary part of the index of refraction times omega over c. Because it's the square of the amplitude, and so that's why I had this factor of 2 in the exponent. Okay? This exponential decay is known as something delicious. It's called Beer's law. I don't know who Beer was. I don't know if he was drinking a beer when he did it, but probably not. He had to concentrate. Okay? So, to the degree, we haven't yet, and we will right now, talk about why in the world is the energy decaying. We just arrived at that by assuming that the susceptibility was complex and or there was a conductor with some conductivity, and both of those went into the form of the complex index of refraction. The real and imaginary part of K are coming from imaginary parts in epsilon. They're also coming from the conductivity. All of that stuff contributes to potential imaginary parts of the index of refraction, and thus this attenuation. So this is known as attenuation. The intensity is attenuated as it propagates in the material if it's not transparent. Okay? All right. So, let's talk now about physical models to try to derive what the susceptibility is. And in the homework, you're looking at the conductivity case, right? So the Drude model tells us about how to relate the current to the field just through the collisions in the material, okay? But now I want to think about what's known as the Lorentz oscillator model. Of a dielectric. Okay. So, beer needed a beer. I need a sip of coffee to get myself through this. All right. So what we're thinking about is, that we can think about, let's just for example think about a gas of molecules, or a gas of atoms, okay? And I want to think about the propagation of electromagnetic wave through this gas, okay? Each molecule I can think about as having bound electrons bound to the nucleus, or the nuclei. Now, the actual description of that, of course, is quantum mechanics. It tells us how the electrons are bound to the nuclei and what the orbitals are, and then we have to do quantum mechanics to see how, when we drive the system with an electric field, how those energy levels are perturbed. I perturb you all the time. But we can approximate that, and we can actually do that from a controlled approximation by a kind of classical model, where we think about this binding of the charge as thinking about it as a simple harmonic oscillator. So we can think about the valence electron that is being excited as being a kind of charge on a spring. And it's really, of course, isotropic, so it doesn't matter. I have it pointing this, it doesn't matter what direction it is, because I can think about it as something which has some electron cloud around it, okay? So I can think about the electron is bound to a nucleus. The electron has some mass, and there's some resonance. All right. So the atom responds, or the molecule responds in such a way that if I drive it at this frequency, I get a resonant response. Okay? If I'm off resonance, well, it's an off resonant response. And in general, the oscillator will damp. The damping can come from various, maybe this is in a crystal, maybe it's not a gas, and then there's background phonons. Or there is radiation reaction, but we'll just say that there's a damping of a harmonic oscillator at some rate. The energy is damped at some rate gamma. Okay? It's kind of the friction in this thing. So this is a phenomenological model that Lorentz, of the famous Lorentz fame, Lorentz transformation, was thinking about when they were thinking about molecules back in the early 1900s. Yeah.
All right, so you said we're modeling it as an oscillator because it's a small perturbation from equilibrium, right?
Right. So the electrons are bound, and when I pull them away, they're going to, so there's an equilibrium position, and to the degree to which I think about that in the classical problem, that there's some potential, the lowest order I can think about is harmonic oscillator.
Okay. And is that Lorentz the same Lorentz from the Lorentz transfer?
It is. It's the same and one and only. It's the Lorentz model of the electron just before quantum mechanics. Right, okay, so with that said, I can look at this gas and say, oh, I have this bunch of molecules, and I'm just gonna I imagine I send in an electromagnetic field. Let's think about it as a plane wave. It's got some electric field, and that's gonna propagate past this atom, or one of the molecules, right? And what's gonna happen is there's gonna be, I mean, this also has a magnetic field, and there's going to be a Lorentz force locally at the atom, okay? Which is going to drive the electron away from equilibrium. So I have a driven force damped simple harmonic oscillator. And so I can write down the equation of motion of the electron. The electron, each one of these electrons has some position as a function of time which is the position away from equilibrium. Right? So I'm pulling this, I'm driving this mass, all right? And so all I have to do is solve the force is ma, and then solve for the position of the electron as a function of time. And given that, I can find the susceptibility. How can I find the susceptibility? So, of course, if I have this electron and it's moving away from the origin, I'm going to induce a dipole. Okay? So what I get from this is I get an induced dipole moment. P as a function of time for a given one of these electrons is minus its charge, because that's the definition of the dipole moment. It's the average position of the charge away from the origin. Okay? So I get an induced dipole moment, and if I have a whole bunch of these guys, then I can find what the polarization density is, which is going to be equal to the sum over all of these guys times some delta functions at the position of the electron. So this is the density of dipoles. Okay. So what I have to do is solve for R and how it responds. How does the displacement of the electron from equilibrium bounding respond to the field? And that response function is going to give us the susceptibility. So let's do it. So F equals ma. What are the forces that are on our system?
Lorentz.
There's a Lorentz force, which is equal to the charge. Okay, so let's set up the problem a little bit more carefully. Let's look at a particular one of these guys. This equilibrium point is right here, and I have an electric field and a magnetic field, which I'll just say is in the x direction and let's call it to be propagating in the z direction. Okay, so it's propagating in free space, and then it's gonna, at some point it hits this. Let's just take this to be z equals 0, because why the heck would we choose it anywhere other way, okay? So the Lorentz force is the charge of the electron times the electric field at the position of the electron as a function of time. And then I also have the velocity crossed into the magnetic field divided by the speed of light. Okay. So that's the Lorentz force that is exerted on this charge given to the local field that it experiences at its position. Okay? And if we have a plane wave, then this thing, these guys have equal amplitude. But the force here depends on the velocity divided by the speed of light. And if that velocity is, if I don't have a very intense field, then that velocity is going to be pretty small. So I can neglect this. And it's completely dominated by the electric force when the speed is small compared to the speed of light, okay? Which it will be, unless we have a huge electric field. If we have a very intense field, I could drive it at relativistic speeds, but let's not think about that, okay? So that's the Lorentz force. What other force is exerted on this charge? The restoring force. We have a restoring force. And that restoring force is minus the mass, omega squared, times its position. Okay, that's the spring constant. What other force is on this thing? The damping force. And if I damp at a rate gamma, then that's m times gamma times the velocity. So that's friction. Okay? And so we put that all together and we get mr double dot is equal to minus m omega naught squared r minus m gamma r dot minus E times the electric field at the position Z naught as a function of time. Okay? And so we get R double dot plus gamma R dot plus omega naught squared R is equal to minus E over M, the electric field at Z equals 0. Now, I was incredibly slow and pedagogical in my derivation of this, but this is something you should just be able to write down. You should have seen this a jillion and 3 times of what is the equation motion of a damped force oscillator. You should just be able to write this down without going through all of these steps. Okay, so I went through them again so we see where it all comes from. This is the equation motion of a damped force harmonic oscillator, where the thing on the right-hand side is the force per unit mass. All right, very good. So we want to solve for the position. Yeah, Don, I'm listening.
So you mentioned that we're not usually going to have a field that can drive our electron at relativistic speeds. So
we could.
right, we
but,
could.
yeah.
We could. So
We had a very high pulse, high intense laser can definitely do that.
right. So that would mean that if we have an increasing omega, we'd have to have a decreasing displacement. So that, because otherwise if we had a fixed displacement that was traveling as we increase frequency, it would have to travel that same distance in a shorter and shorter amount of time. And so if we,
Well, this is all locally, I'm not quite sure about, here, I'm just at this position of the electron.
Right.
And, I mean, it's really a question of if the electric field stretches the thing so fast,
Right.
then eventually I'm gonna, in addition, I'm gonna have, this is gonna exert actually radiation pressure on the individual atom, because the force is gonna be, maybe let's take that question after the fact. I wanna,
Yeah.
let's, so it's kind of an aside, let's discuss it together. Okay, what I wanna do is I wanna solve for what is the position and therefore the induced dipole moment, okay? So we know that what we're, in this case, our electric field would take it to be a plane wave. Okay? So at z equals 0, I see some oscillating electric field. So I'm sitting here and I'm going to see the electric field pushing on me, and it's pushing on me at this frequency. Okay? Mechanics 1. I have a harmonic oscillator. It has a natural resonance frequency. Okay? See it? There it is. Now, I'm going to drive the system with some frequency, which is not necessarily equal to the resonance frequency. What's going to happen to the oscillator? Yeah, so it's going to oscillate, and there'll be some transient response due to the fact that there's damping, but then after a time that's a little bit bigger than 1 over gamma, it'll come to steady state. And it'll have a steady state oscillation with some amplitude and phase. Question. In steady state, okay, we go back to mechanics 1, I don't know where you were, it was COVID. In steady state, at what frequency does the oscillator oscillate if I'm driving it at frequency omega? Remember, this thing has a natural resonance frequency, omega naught. It's the resonance frequency, and I'm driving it at some other frequency. It could be on resonance, but it might be not. At what frequency does it oscillate in steady state? Omega naught or omega or something in between?
Omega.
Omega. It oscillates at the driving frequency, right? I mean, here's my thought experiment. This is the resonance frequency. Now I'm driving it like this. The spring is gonna go at the frequency that I drive it at, not at the resonance frequency. Okay? I just did an experiment. Very proud of myself. All right. So with that, what we know, if we know in steady state that the position of the electron is oscillating at frequency omega, then we know that the steady state motion is of this form. Because anything that's oscillating at frequency omega is of this form. And thus, we can solve this equation in steady state without, different equations. Oh, there's a homogeneous solution, a particular solution, etc. If we're just interested in the steady state solution, we just plug this in. And thus, we get so given the fact that we're forcing it with this electric field that has a single frequency, the steady state response will be at the same frequency for a linear oscillator. Now, nonlinear optics, that's a different thing, but for a linear response, it will be at the same frequency. And so I can plug that in, that ansatz, into this equation, and everywhere I see a time derivative, I get a minus I omega. So that becomes minus omega squared R tilde minus I omega gamma R tilde plus tau omega naught squared R tilde is all times e to the minus I omega t is equal to minus charge of the electron over m d0 tilde e to the minus I omega t. Everyone see what I did? I just plugged in the ansatz, and wherever I saw a time derivative, I replaced it by multiplication by minus I omega. And so I turned my differential equation into an algebraic equation. And so I can now solve for the amplitude, which is the solution, and that's equal to E over m divided by omega squared minus omega naught squared plus I omega gamma. Okay? And so what this tells me then, given this, it says the electric dipole moment will oscillate as well with the frequency omega. And so that tells me that the electric dipole moment is equal to minus E times R oh, I shouldn't have gotten rid of my minus sign. Minus. Yeah. Then I'll have an E squared over m divided by omega squared minus omega squared plus I omega gamma. Okay. And so what this tells me is that the induced for a linear oscillator where the restoring force is proportional to R tells me that the induced dipole moment will be proportional to the strength of the electric field. And that proportionality constant is a complex number, which we call alpha. And alpha is what's known as the polarizability. In this case, the atomic polarizability. Think about it as an atom or a molecule. It's telling us how polarizable, how much dipole moment do I get? What's the amplitude of the dipole moment given an electric field strength? Yeah.
So you mentioned for linear, you get the ansatz we had, where it was RT is that. For nonlinear, would we get that plus harmonics?
That's correct.
Okay.
So if I had something that was proportional to the squared, I can get harmonics. So that's how I get harmonic generation, indeed. But let's, for the moment, just focus on the linear case. Okay? Yeah. So, what this tells me, again, if I were to ask, what is the real dipole moment? Let's just take this to be linear polarization for simplicity. I'm not so simple in the homework. What I get is E0 times the real part So, whereas the electric field at the position of the charge is oscillating like cosine, the dipole has a part that's oscillating in phase with the electric field, and a part that's oscillating 90 degrees out of phase. It has a phase lag. And the amount by which it has this phase lag is related to the imaginary part of the polarizability. If there had no damping here, then this would be purely real. But the fact that it has damping means that there's a phase lag here. Okay? The electric field, to the degree that this is linear polarization, is E0 cos. But this has a part that's in quadrature. In quadrature means it's 90 degrees out of phase. There's a part that's in phase and a part that's in quadrature. And the part that's in quadrature depends on the imaginary part of this. So with that said, let's take a look at the polarizability. And let's define what we call the detuning as how far off resonance I am. Okay, so I'll define delta to be the difference between the driving frequency, the frequency of the light, and the resonance frequency of the molecule. Okay, if delta is 0, we say it's red detuned. I mean, if delta is negative, it's red detuned, it's below resonance. If delta is positive, we say it's blue detuned because it's above resonance, okay, if delta is positive. So let's rewrite this as equal to, this is equal to omega 0 minus omega times omega 0 plus omega, which is equal to delta plus omega naught, and this is minus delta. And so, and omega here is equal to omega naught plus delta. So that tells me that the polarizability I can rewrite as E squared over m minus delta times omega naught plus delta minus, is it minus or plus? What did I get? Plus. Okay, and let's look at the behavior of this when I'm close to resonance. So let's say that the detuning is much, much smaller than the resonance frequency. So this is a near resonance approximation. Then my polarizability is E squared over m minus I delta plus omega naught gamma. Oh no, this is, yeah, sorry, let me rewrite this.
Shouldn't it be a 2 omega naught in the first term in the denominator there?
Here?
Yeah.
Yeah, right, so that's right, thank you. Okay, so let's just write it, let me write it out, delta, plus 2 omega naught, plus I times omega naught plus delta gamma is approximately equal to E squared over m 2 omega naught minus delta plus I gamma over 2. Okay, so that's under this approximation that delta is much, much smaller than omega naught, I get this form of the polarizability. Okay. Which is equal to E squared over 2m omega naught times the following minus delta. So near resonance, the polarizability is approximately equal to E squared over 2m omega naught minus delta over delta squared plus gamma squared over 4 minus I. Got my signs wrong, but there should be a minus. I'll come back, I have to fix this. This is all messed up. So minus I. So minus I here. So minus I here. Plus I gamma over 2 delta squared plus gamma squared over 4. I want to just conclude briefly. We'll get all the algebra right next time, but I want to just quickly take a look at this polarizability. And I'm going to look at it as a function of the detuning. And what I find is the following form. The polarizability has a real part and an imaginary part. The imaginary part has this form. This curve is known as, for reasons that are obvious, a Lorentzian. At delta equals 0, it has some height. And when delta starts getting big compared to gamma, it falls off, and it falls off algebraically like 1 over delta squared away from resonance. The real part of alpha has this form, which falls off like 1 over delta away from resonance. Right on resonance is 0, even though I didn't have it cross at 0. But if I'm far from a resonance, the real part dominates over the imaginary part. Near resonance, the imaginary part dominates over the real part. The real part of alpha is related to the real part of the index of refraction. The imaginary part of alpha is related to the imaginary part of the index of refraction, which means if I'm close to resonance, I'm going to have a lot of imaginary part, which means I'm going to have a lot of attenuation of the wave. If I'm away from resonance, then I am dominated by the real part, which means the material will be highly transparent. I will have an index of refraction related to the real part, but it will be highly transparent. I will have very low attenuation. So let's just conclude with the following question. Why does the wave become attenuated physically? What happens to if the wave is being attenuated, that means energy is being lost in the wave. Where the heck did it go? Yeah, it went into the driving of the material and the fact that there was a damping. If there was no damping, I wouldn't have this at all, okay? So somehow the energy that is put into, it's in the wave that is driving this oscillation is not going back into the wave, it's going somewhere else. It could be going into heat. It also could be going into scattering. I could attenuate the wave because it's scattered into other directions. That's typically what happens in an atom, because it's not like there's vibrations and other things. The energy comes into the atom and then it gets re-radiated and thus scattered. So I can have attenuation by heat or attenuation by scattering. But the bottom line is the energy goes into the material and it doesn't go back into the wave, the propagating wave. It goes into other degrees of freedom, and thus we get attenuation. So the imaginary part of this is related to the energy that is being absorbed. So this is related to absorption. Whereas this is related to dispersion, and we'll pick those 2 points up next time. All right? Isn't that cool? Have a good rest of your day.